Welcome back, everybody. Welcome back to the channel. So today we're going to pick up where we left off, where we're talking about how to parse self-expressions. Today we're going to talk about parsing base expressions. So basically what a base expression is, here I'm going to go to our file again. What is it called? Syntax.sharp. Basically what a base expression is, a base expression is the opposite of self. So we already know what self is. That basically forces the compiler to look for elements inside of the current class. Well, base class is simply the opposite. So I'm going to create a class called B here. And B, let's create some field. So we can say size, right here, I'll put count. So count, it's an int. And then we can create that same variable inside of our class here. So let's say this is class A, and it has a base class of class B. So if they both have count, we have to be able to allow the user to figure out or force the compiler to pick which one they want. So, I mean, under normal circumstances, there's going to be a certain flow, which we're going to see later on in the compiler. So basically, the compiler has a certain flow that it looks for when it comes to resolving information. So the first thing it tries to do is it tries to find locals. Now, obviously, you're not in a function, so there's no locals to be found in this context. But if there were locals, we would search locals, and then after that, we would start searching the class for like fields and the current class, and then we would start looking at the base class. So because of that, we need the base function to basically say, I want to get the count variable in the base class. So there's going to be a couple formats for base. So first you're going to have just the regular base. So same thing like self. This is just going to return the base class of the actual class. This is going to return the instance of the base class. This doesn't really mean anything. I mean, it's kind of a useless feature, to be honest, because instances all live inside of the same object. And we'll go over how the memory model is in terms of at the low level for classes and objects later on. But basically, all you need to know, like when we create this class, all we're effectively doing is when we create class A that has a base of B, we're basically saying class A, which doesn't have any base classes. Like base classes are just a construct, like it's a high level construct. But when it comes to actually modeling the memory and how it should be stored on the actual machine that the programming language is running on, we're going to have to say something like a underscore count, which represents the int variable in the a class, and then b underscore count, which represents the count in the B class. And this is going to be the memory model of the actual class once we compile everything down. So returning base is effectively not going to do anything. It's basically just going to return self, which is the exact same function because the entire instance of the object you can see here is just one object. So, but just wanted to kind of put that out there. After that, of course, we have our base with a pointer and count. So we have that. So basically, the compiler is going to go up one level. So it's going to go up to the base class, and it's going to access this count variable. Now, as usual, when you're developing a compiler, you can't just do the bare minimum. You have to support everything. And sometimes there's both legitimate and illegitimate reasons why something may or may not happen. This case, I think there may actually be good use cases for it. So like, let's say, I'm going to give an example here. Let's say we have a class called C, right? And now, I mean, like this is a extreme example, but it could happen. Technically, if something can happen, you should support it. So we're going to create this class here, and we're going to force the class B to implement class C. Now, every single class has a count variable. So if you just do this, well, based on how I know how my compiler actually works, which one of these is it going to return? Well, it's going to return this one because this is the closest variable in the current scope. But if we do this, self.count, that's going to return, again, it's going to return this. However, if we were inside of a function, like if we were inside of a function called foo, here I'm actually going to create it right now. Why isn't my mouse working? Define foo, and we want to have like some variable. So we create some variable here, and we want to infer the value by assigning it to count. Now, if we create above here a count variable, and we assign that to the value of 0, well, then it's going to basically grab this variable. It's not going to grab this one, so that's why we need to say self.count, so it's going to completely ignore this and access this. But what if you have a situation where, as you see here, we have multiple counts and multiple classes? You need to specify which class it's going to come from, so you want to use the at symbol. So we're going to say base at C, and what that's going to do is that's going to get the count variable at the C class. So again, this is one of those things that's probably not going to happen in practice, but it's a good thing to support because there could be a situation where this is useful. So let's go into the parser and see how everything is compiled. So when we start parsing our base class, we're going to, of course, need to expect our base token. After that, we want to parse what's called a base class utype. And what that effectively is that is this part. So for every time we parse a base, you have an optional base class utype, which basically denotes that this is the class that I want to derive the information from. So here I'm going to go to base class utype. And all right, so we can see here we have the at symbol. And the at symbol is, of course, this symbol here. So if we have the at symbol, and if you notice, it's not required. So we just check to see if it's there. If it's there after we parse our base token, then we say, okay, let's create a base utype. So we create that branch and we consume the at symbol. Of course, we do not need this token, so we just ignore it. We don't add it to the actual branch. And then we just parse a utype. And I mean, that's pretty much it. It's pretty straightforward. So we'll just parse this. And of course, it'll stop at the arrow symbol here because that's not a dot. So what this allows you to do is this is why utypes, you're going to start to see in my programming language, utypes are very powerful. It allows me to hook in a ton of functionality that already exists. So like because of this, you can effectively do like std hashtag. So you can put like the module name and you can say std.io.thread or something, right? And then you can say c.innerClass dot some other class, right? You get the point. So you can do that. You can also do some inner class. So like you can do generic types. You can say this inner class of var, right? So you can basically add all of this parsing functionality just by calling parse utype. So this is a very powerful feature that I added for picking which base class you want to get the information from. So once we do that, then let's go back up to base. So after we parsed our base class utype, we expect the arrow symbol here. And then we parse a dot notation call expression. Now, you guys know what that is. What that's going to be is effectively this. So like we can say base.count, we can say base.foo, right? Like if we have since we're specifying C, you can say define foo. Right now, this is a more probable example, right? Like it's probably not going to happen when you have like the same variables all created in the same class. That's kind of silly, but like maybe you have overloaded functions and you want to pick which function you want to call from which class. Like this is a very good way of doing that by using the existing utype functionality or the technology for parsing utypes and then also parsing dot notation call expressions. And as we saw, they can get pretty complicated by accessing a field and having an array here and then calling something. So, when you pair all of this stuff together, you get some pretty complicated syntax. But the premise is pretty simple based on how we are parsing everything. So This is how you can really allow your language to start to grow in terms of complexity by just hooking in a bunch of different things. So after that, we want to encapsulate our data into a base class expression, and then we want to add our after expression. So you guys know what that is. Like let's say we have, I don't know, count, and we want it to represent it as, some other variable or some other class. We can say as integer of type underscore int 32, I think, because int class represents a int 32. If you use long, that's an int 64. So you can just basically cast it down one level to this class here. So that would be an example of what you would do. But yeah, so in this example, this is kind of similar to the self example here where I peek to see if the next token is not equal to as. And if so, then we basically process everything and we just immediately jump to the thing that we need to process. Um, and if it's not equal to as, of course, we reset the branch to the last sub AST. Get last sub AST. Same thing for, oh, and that was actually a bug. So you can see here, I'm getting the sub AST of self E, but it should be base. So I just fixed the bug. Interesting. But yeah, so you want to reset the branch if it's not equal to as, because when you get down to parsing an as expression, you will see here that we need to basically have a left expression, and then we need to have a right U type, or so you need to basically have like two ASTs inside of the branch. So that's why we do not reset the branch if we have an as. So you can just copy this down. This is exactly the same code that was up here for self-expression, and I already explained it yesterday, or the last video, so I don't think I have to go over this again. But yeah, so let's see how all of this is hooked together. So I'm going to go to parse variable declaration, go down here and see what happens. So we're going to do a couple of different formats. I'm going to delete all of this code and say base. All right, so we look here, we can see what was actually generated. So if we have our primary expression, we have a base expression of base with this symbol here. You don't need this symbol. I don't know why it was added. I'm pretty sure I told the compiler to not add that symbol. But we do not need either of these tokens, so you can ignore them if you want. And then we have a dot notation call expression, and we already know what that is. It's just currently an identifier of a reference pointer of count. Now let's see how the expression looks if we just say base. All right, so I just found a bug I was going to show you guys the formatting for this, but I just found a bug with this. So basically what it's doing is it's basically forcing the user to have this arrow and then a dot notation call expression, which effectively generates a empty AST with no information in it. So in order to fix that bug, we need to do a check here and say if peak at 1 is equal to the arrow, then we can process what we need. So, and here I need to dereference the pointer. So if the next token is in fact equal to the arrow, then we want to expect the arrow and call a dot notation call expression. Otherwise, it's not really, it's not required. So we can just do that. Also, we can do other things. Like we can say base at B, right? So of course, we can have the at symbol, which will basically force the compiler to return a certain class. But yeah, so that's how you fix that bug. Quick and easy one. So let's check again to see how everything looks. So if we have the example where we have our at symbol, we have our primary expression, a base expression. Oh, AST unknown. Okay, so I need to fix that. But that should be our AST. Here, let me go back to parse expression and go to parse primary expression, go down to parsing a base class. All right, so this should be our base U type. So that's what the unknown is, and then we have our U type identifier reference pointer of B. So that's pretty simple. Now let's look at the case where we have count. So we want to get the count variable inside of this class. So if we look here, we have our primary expression, base expression. We have our pointer here. So actually, you know what? Never mind. I take this back. I was just looking inside of my compiler. We do need this pointer token. So that's why it's added there, because I actually checked to see if the pointer token is there. And if so, then we do a dot notation call expression. Because otherwise, if you remember, if there isn't a pointer, we can just return whatever class we're referencing here. So we do, in fact, need the pointer. But if we look at the example where we have the pointer and the count, again, we have our utype class or our base utype of b, and then we have a dot notation call expression of count. So there's that. And yeah, so that's going to be it for today, guys. This video is a little bit shorter. The next video, we're going to be going over something pretty big. So we're going to go over a little bit of parsing a dot notation call expression. We've already pretty much, like you guys, I'm pretty sure already know how to do this, but I'll just go over it one more time. And then we can look into parsing new expressions, which that's going to be a lot of fun because I have several different variants of new expressions. So this one's going to probably be a much longer video. And yeah, we're almost done with parsing everything in our expression. We just have a couple more things to parse and we can be done with this. Guys, the language tutorial series is coming together. Pretty soon we're going to be working on the compiler side. So this is going to be a ton of fun. I'm definitely excited for it. As usual, if you guys have any questions, definitely write them in the comment section below. And of course, if you guys would love to help support the channel, I would definitely recommend heading over to my GitHub repository at andrewdevcd/sharp. When you get there, you can definitely watch, star, and fork this repository. That's going to give this programming language a lot more visibility and let other developers know this language exists. Also, if you're interested in what are some of the things that I do on a daily basis with the language, as far as like updates or anything, you can check out the remastered branch. Pretty much anything other than master and remastered are not used, so keep that in mind. This is the main branch where I update things. And if you go over here to my commits, you can actually check each commit and see, like I write some pretty wordy comments. So you can kind of get a gist of what I did in each commit as far as updates go and without really having to look at the code. Now, I haven't done an update in a while. I'm really trying really hard for you guys to get the virtual machine up to a pretty good state. I got some really cool stuff that I added in there recently, so hopefully I can get that update out pretty soon so I can continue the YouTube series and there doesn't have to be any delays. Also, if you guys are interested in maybe learning about things that I've done in the past to the language, or maybe stuff that I'm looking to add into the future, I would definitely recommend you heading over to the docs folder. And there's going to be two main files that you can look for. One's going to be the changeless file, which is going to pretty much hold everything I've done to the language in the past, as far as updates, bug fixes, so on and so forth. And you can check out the roadmap file, which is going to contain pretty much anything that I've done in the past, as well as stuff that I'm looking to add into the future, as far as like language improvements or maybe syntax changes, pretty much anything and everything in between. So that's going to be it for today, guys. Definitely like, comment, and subscribe if you guys like what you saw and you want to see more. Until next time, I'll see you guys later.